Research Center. He received his bachelor degree from the Department of Mathematics at National Tsinghua University. After that, he obtained his PhD from the Department of Physics at National Taiwan University. His research interests include quantum algorithms and quantum complexity theory. Let us all welcome our speaker.
Okay, thanks, Lincho, for the nice introduction. So this is our work on testing sign graph clusterability. And this is a joint work with Simon Epers. And so let's begin from the outline. So first of all, I will give you some introduction of the graph property testing and the special property, which is clusterability in sign graph. And we will show you the main results. And actually, the main result contains two folds. The first is we derive the query law bound, classical query law bound for testing the clusterability. And the second result is we propose a quantum algorithm which outperforms the existing classical clusterability tester. So this is our two main results. So let's begin by introducing the problem. So what is the graph property? Let's consider actually graph property is something that we are given a graph and we would like to see or to test whether the graph satisfies a certain property. We would like to use a simple example to demonstrate what is a graph property. For example, we all know what is a bipartite graph. If a graph can be decomposed into two components, such that there is no edges connecting vertices in the same component, like this instance, then we call such a graph the bipartite. Okay, and by now we are given a graph, and we would like to check whether the graph is bipartite or not. And the bipartiteness is actually a quite famous graph property, which can be applied in the web search engine. And there are multiple graph properties, such as expander. This property can be used to estimate the converge rate of Markov chain Monte Carlo algorithm. And for example, the main topic of this talk, the clusterability, it can be used to analyze some social network. So let's go back to the bipartite. Now we are given a graph, and the natural question is, how many queries are required to test the given graph is bipartite or not? Okay, the answer is we need at least n queries so that we can see the graph is bipartite or not in an exact manner. For example, if we are given a graph like this, we have an edge here, and so we know the graph is not bipartite unless we make a query of these vertices. So in other words, we have to make a query to every vertices in the graph so that we can see the graph is bipartite or not. Okay, So the question is that whether we can use less queries to verify the graph is bipartite or not in an approximate manner. For example, so let's assume this is a given graph, and if we can allow, if we are allowed to remove this edge, so such that the graph is become bipartite, and that is some we call a close. Then we can call the graph is close to bipartite. And if we are consider such a approximate approach, then we only require square root of n queries. Then we can test the graph is bipartite or not in the approximate manner. So this is the main idea of graph property testing. So in order to formally introduce such a testing problem, we are introduced the graph property tester.
Sorry. Before you move on,
okay.
Can you remind me why the classification of a bipartite graph is important to your case? Why you need to check it is bipartite or not in the query and web?
Oh, why we need a n query to see to check the graph is bipartite or not? Do you mean that?
I mean, what you mean bipartite? You mean bipartite between query and website or the graph? What's the bipartite you mean here?
Oh, sorry. You can ignore the website search. Bipartite is that if we are given a graph, and we would like to check whether we could decompose the graph into two components, such that there does not exist an edge in these two components. There's no such an edge. So the edge can be found connecting the vertex belong to distinct components. So if a graph can be decomposed like in such a manner, then we call the graph is bipartite.
So you need the complexity n to check whether it's bipartite for classical algorithm.
Yes.
Okay, thank you.
And I think it's also for quantum algorithm. If we would like to check the bipartiteness in an exact manner.
Then what's the square root of n about?
Yeah, it's exact. If we are allowed to, for example, if we have an edge here, if we are allowed to remove a few edges from the graph, such to make the graph become bipartite, then we call the graph is close to bipartite. For example, I think I can skip the to the definition of bipartite. Now, the bipartite is that if we could decompose the graph into two components, okay, such that there's no any edges in each component. Okay, we call it as bipartite. So for this graph, for the second graph, we know that it is not bipartite. since we can find an edge in this component, right? However, if we are allowed to move this edge, then this graph become bipartite. In other words, if we could, to generalize this idea, if we are allowed to remove a few edges to make the graph become bipartite, we call it is not far from bipartite or close to bipartite. And there is another scenario. If we have to remove a lot of edges to make the graph become bipartite, then we call it far from bipartite. Yeah, so this is the three conditions. Bipartite, this is for the bipartite, and this for the not bipartite, but close to bipartite. And this is far from bipartite, which means we have to remove a lot of edges. And a lot of edges means we have to move the number of edges that have to we have to be removed or added is proportional to the number of vertex in the given graph.
I see. Thank you.
Okay, thank you. So the graph property testing is that we would like to test the graph in an approximate manner, so that the tester is actually a randomized algorithm, which take the input of the graph and an error parameter epsilon. The algorithm have to return, accept or reject if the graph satisfies this property, the algorithm will always return accept. On the other hand, if the graph is far, if we have to remove or add these at least that many of edges to make the graph satisfy this property, then we call the graph is epsilon far from this property, and the algorithm have to return the reject. Okay, so it is a yes or no question. We are given a graph, we have to test the given graph satisfy a property or far from this property. Okay, so yeah, so that's why we call the property testing is can solve the testing problem in an approximate manner. Okay, so now
just a question.
Okay.
What is the D?
Oh, sorry. The D is the okay. We are given a graph, and for each vertex,
it's a degree. Oh, okay.
Yeah.
I see it there.
Yeah. The degree of the
Oh,
graph.
sorry. But on another question, I see that you have this quantity that is the epsilon, N, and D, right?
Yes.
But you call epsilon far.
Yes.
Why is that?
Oh, since since N and D is given by the problem. N and D. Yeah. And we in most cases, we assume that the D is not proportional to N, and D is a constant that is independent of N.
Okay.
Yeah. is a fixed number. So yeah.
Okay. Thank you.
Thank you.
Sorry, another question.
Okay.
I don't quite understand what's the property P you mean. I mean, I do not see the bipartite words here. You mean query access to the graph? I mean, how it is the property satisfied? I don't really understand. Yeah.
Yeah. The P can be any graph property. It can be bipartite or clusterability, which we will introduce its property later, and the expander. And there are a lot of graph property. And here I just list three quite famous graph property in this slide. So the graph property P can be bipartite or clusterability, or the expander, or some other graph property. Yeah.
So you mean given some, for the algorithm it means that given some number of query access to the graph, can you decide it satisfy this property or not?
Yes.
Okay, so for different property, the number can be different. Okay, I see.
Yeah.
Okay, thank you.
Thank you. So okay, so we have introduced what is bipartiteness, and actually we have a optimal classical algorithm to solve it, and so by now bipartiteness is a closed question. So now we are more interested in the clusterability for sign graph. So there are two words. One is clusterability and one is sign graph. So what is a sign graph? We all know what is a graph. Well, a graph is can contain the vertices and the edges which connect vertices. And if we are allowed to assign each edge we call a sign, which can be positive or negative. Okay, then we can call the graph is a sign graph, which means if we remove this labeling, the sign graph is just a normal graph. And if we label each edges, so each edge a label, then we call the graph is a sign graph. So I think sign graph is not it's quite easy to understand. And so what is a clusterability? Okay, this property is quite close to bipartite. Okay, now we are given a graph, a sign graph. If we can decompose the graph, the sign graph into several components, such that in each component there can only in each component it can only contain positive edges. This is positive. It is positive. And the negative edges can connect vertices belong to distinct components. Okay, if we can decompose a sign graph into in such a manner, then we call the sign graph is clusterable. And this is the clusterability. Okay, so this is the property is quite similar to bipartite, or but here we I have to mention that this is a unique property for sign graph, since in a normal graph we do not have the structure for labeling of the labeling of the edges. Only in sign graph we have the labeling, and so that we can define the clusterability. Okay, this is the formal definition for clusterability. Yeah, but I think the schematics is more clear to introduce this property. So by now we introduce these two.
Sorry. Can you remove the left bottom corner of the screen and just get? Oh yeah. Thank you.
Okay. Okay. Thank you. Okay. So by now we have introduced the bipartiteness and the clusterability, and we did some previous work here. Okay. So for the classical upper bound, which means there exist algorithms to solve bipartiteness testing in square root of n times, also in square root of n queries, as well as expander and the clusterability. And this work is actually the work from my cooperation, Simon. And however, we do not know what is the classical query law bound. However, we indeed have the classical query law bound for bipartiteness and expander, which proposed by Gorich. And this law bound implies these this algorithm are optimal. So our target is to show the classical algorithm is optimal. So this is first our main result. And our second result is we propose a quantum algorithm which outperforms this classical algorithm. In other words, we demonstrate the quantum advantage for the clusterability testing problem. So this is our result. We show the classical query law bound for testing clusterability require at least square root of n queries. And we propose an algorithm which can solve the testing problem in n to the 1/3 queries. Okay. This is our main result. So let me introduce our first result. The classical query law bound for testing clusterability. Okay. So this is the theorem, and the main idea is that in order to prove the query law bound, we could decide a hard instance. So what is a hard instance? If we have two families of graph, or we could say two sets of graph, such that the graphs in we call G1 are all classable, which means the graph in G1 satisfy the property as we have discussed in this slide. Okay. And the G2, most of the graph in G2 are far from classable. Okay, if we can design such an instance, And we would like to show G1 and G2 cannot be distinguished with square root of n queries for any classical algorithm. Then we can show combine these two lemmas. We know there is no classical algorithm could test clusterability within square root of n queries. Why is that? Since if there exists a clusterability tester which can identify a given graph is clusterable or not, then it suppose can distinguish these two families of graphs, since they have a distinct clusterability property. So if there's no such an if there's exists such a clusterability tester, then it can distinguish these two this property. Then it will contradict to the to this statement. So in another word, we would like to show we would like to introduce how we construct such the set of graphs. Okay. So this is our main technical contribution. There exist two families of graph, G1 and G2, such that the graph in G1 are far from clusterable and with a very high probability, which is 1 minus some exponential small number. And the graphs in G2 are all clusterable. So how to do that? Now we are considering a set of vertices, which and each vertex is labeled a parity, which can be even or odd. Okay, and for the vertex with even parity, we use the black dot to note it is even, and we use the blue dot for labeling the odd parity. Okay, and by now we are considering a sign graph. So each vertex is labeled positive or negative, and we use the green line to identify the positive sign edges, and use the red lines to identify the negative signs. So so for G2 contains one Hamiltonian cycle, and in such a manner, each negative sign is adjacent to vertices with distinct parity. So we have the even parity, even odd, even odd, even odd, and so and that in such a manner. Okay, and it also contains some edges which are labeled positive, and these edges connect the same parity vertices. For example, we know the black dots represents the even parity vertices, so we could find that these edges connect them together. Okay, and the G2 contain 4 such and cycles. And we know that the graph in G2 are all clusterable. Why is that? Since we can decompose this graph into two components. In the first component, it contains all even parity vertices, since they are connected by the positive edges. They are connected by positive edges. Okay, so we have two components. And the negative edges can only connect vertices with distinct parity, which means these two components can only be connected with the negative sign, with the edge with negative sign. So the graph in G, so the graphs in G2 are all classable, since they can be decomposed into two components. Okay, and such that it satisfies the clusterability property. Okay, so for the G1, we would like to show why it is why the graphs in G1 are far from bipartite. Sorry, far from clusterable with a very high probability. Okay, this is the proof stretch for why the graphs in G2 are classable. And to show the graph in G1, to show the graphs in G1 are not classable, we could observe that we are given an instance of graph in G1. Okay, and we know that if we would like to make the graph classable, we have to remove some cycle edge, some cycle positive edges. Otherwise, we have to remove every negative edge. Why is that? Since we know that in the clusterability, in the property of clusterability, the positive edge can have to connect. Sorry, the component. So the positive edges connect every vertex into one component. So in order to make this graph classable, we have to remove each vertex in each edges, each label, each red line edges, or it will contradict to the clusterability. So let's assume we remove X cycle edges, which is a number smaller than epsilon ND edges. Since if we remove epsilon n more, if X larger than epsilon ND, then the graph is not classable. Okay, so we have we call X cycle component, and by the definition of the graphs in G1, we have another we have edges that's connecting these vertices, which means this cycle component will be connected by the green edges. So it's become one component. In other words, the graphs in G1 are not classable. Okay, and this is the main idea to prove this lemma. So So next I will introduce the clusterability testing algorithm. Okay, this is the formal description for the theorem. We have a quantum algorithm for testing clusterability with n to the 1/3 queries. Actually, we use the quantum collision finding algorithm to design an algorithm to speed up the existing classical clusterability tester. So, what is the collision finding algorithm? Let's consider we are given a function which maps a set x to another set y, and we also have a symmetric binary relation. Okay, then there exists a quantum algorithm that can find a distinct pair x and x prime such that they share f of x such that okay, this pair satisfy this binary relation, okay, within that many queries. Okay, this is the collision finding algorithm, and if we only if for classical we need that many of classical queries, but for quantum we can speed up in yeah, the number of queries is we call the size of x to the 2/3. So now we are using the collision finding and the classical clusterability tester. So the tester is proposed by Simon. The statement is that we have the classical algorithm to test clusterability with square root of n query complexity. The the procedure, the main idea of the algorithm is that now we are given a sign graph, and first we sample a vertex in the graph, and we implement multiple random walk, and the number of random walk is proportional to square root of capital N, and such that the random walks can only pass the positive edges. For example, like this one, we do the random walk, or this one, we implement a lot of random walk. So for example, this for the first walk, and we have the second walk, and we have a third walk. Okay, something like that. We implement that many of random walk, and if we could find one negative edge between these positive walks, then we know the graph is not bipartite. Also, it's not classable. And in this theory, they show that the graph is far from classable with a very high probability. Okay, so this is their main result. So
sorry, in the algorithm, the random walk algorithm, you show how different, how do the different walks start? You just pick start from the sample of vertex S and just random walk many different times. And how do the random walk stop?
How do the random walk start?
Stop.
Oh, when? Okay, the length of random walk is poly 1 over poly epsilon. The epsilon is the error parameter for the clusterability testing algorithm.
So it just stop around this length. It does not stop when it meets some certain type of vertex. It does not like that, right?
Yeah, it just do the random walk along the positive edges and such that the length of the random walk, for example, the length of random walk for the purple walk is 1, 2, 3, 4, 5 is 1, 2, 3, 4, 5 is 5. So the length of the random walk is proportional to 1 over poly epsilon.
Okay.
Yeah, it's independence of n, capital N, the number of vertex in the graph.
Okay, I see.
And of course, if we can find a negative edge connecting this walk, for example, we do some random walk like this, and we can find a negative edge, then we know the graph is not classable. Why is that? Since we know we know there are multiple vertices and they are connected by the positive edges. So they are in the same component by the definition of clusterability. However, we can find a negative edge connecting some vertices between them. Then we have to we know it's the graph is not classable, and they show that if we implement that many of random walk with such that each random walk has this length scale, then the graph is far from classable with high probability. Yeah, that is the main idea for their algorithm.
So you check whether the two different works are connected by negative edge only at the end of each work. You don't check.
We don't need to check the we can check every. We can check. Sorry. For example, we can check this or this if there exists such an such a negative edge. We can check.
So that then is still complicated. I mean, there are many different works, so you need to check every one of them at every step. So it's still complicated.
You mean this algorithm?
Yes, because it's not only two works. It can be many works. And at the order of square root of n, and you need to check if every vertex along the vertex are connected to the other works. So it's still complicated, right?
You mean
because you only check the two.
I know what you mean. Since the length of the walk is, we can say, small, since it's independence of capital N. So okay, so you can imagine that you have multiple walk. And you implement, oh, I know what's your question. You mean you have to check? Yeah, actually the question can be fixed by using the lemma in. I did not mention that lemma in this talk, but it can be fixed by using the lemma in Goldrich's work. I think in 1 or 2. Yeah. You mean you still have to check this, right?
Yes.
Yeah, it can be fixed by using some lemma in Goldrich's paper. And yeah.
Okay, I see. Thank you.
But the main point is that we have to actually you can imagine that if we do, okay, now we are here, we do a random walk, we are here, and we make a move like here, like here. Okay, so the edge is positive. Then in each procedure, we can make a query to the vertex. We can make a query to every edges connecting to this vertex. And if that vertex is content in some other work, then we just find these negative edges, or this negative edge. Does that make sense?
Yes, it makes sense. Thank you.
Since whenever we make a random walk, we check the vertex adjacent to that vertex. Okay, so the time complexity is actually dominated by the number of random walk. So that's for the chi-square algorithm. And our main idea is that we would like to translate the finding of a negative edge to the collision finding. Okay, if we can translate, so for example, if we find a negative edge, then we find a collision. So the time complexity, so the query complexity can be improved by using the quantum collision finding, which give us the n to the 1/3 query complexity. Since n square root of n to the power of 2/3 is equal to n to the 1/3. So yeah. For example, in our main idea is that we define okay, like this one. We define finding such a negative edge by finding a collision. So we can use the quantum collision finding, then we could have our second main result. Okay, this is the main idea for designing the quantum algorithm for testing clusterability. And yeah, that's all. Any questions?
All right. Thank you for the presentation.
Thank you.
I have one, I guess, because are you putting the plus and minus edges because you're considering like the bipartite scenario?
Oh, you mean
Yeah, because you put the sign graph, right?
yeah,
And
yeah,
then each edge in the graph is going to have a plus or a minus to represent it.
Yeah.
Is this the case because you're interested in a bipartite scenario?
No, actually, we are considering the clusterability, which is quite different from a bit of difference from bipartite. Since in a normal graph, we each edges is identical, no labeling, positive or negative. Then we cannot define such a property.
No, I ask because this reminds me when you have graphs that have weighted edges.
Yes.
So I was wondering why you put, like, let's say this two different weights
Oh, it
and
depends
not more.
on the scenario of the application scenario, I think.
Mm-hmm.
Yeah, for example, if we are considering the traveling salesman problem, we have to consider the weighted graph, the edge weighted graph. And actually, in some scenario, we prove the weight on the vertices, but in this scenario, we only consider the graphs. The edges are labeled positive or negative.
Mm-hmm.
So I think that's quite depends on the scenario that you would like to apply.
And does your results extend if you have more labels?
So then if we have a more label, can our algorithm be valid or
Yeah.
bound? I am not sure for the lower bound.
Mm-hmm.
But I think we can still have a similar result. Yes, but for the quantum algorithm, I think if we have if we have multiple labeling, then we have to define some property which is distinct from clusterability.
Mm.
Since for clusterability we are considering such a whether we could decompose the graph into in such a manner. We have two labeling, and if we have multiple labeling, we have to define some other graph property.
Okay.
Yeah. Or we could say we could define another property. Yeah.
Okay. Thank you. Do we have more questions?
I want to ask how you actually apply the quantum collision algorithm to the clusterability. Because you need a relation for the collision algorithm. So the relation you mean here is the negative sign, right? Between two vertex, if they have negative sign or not.
Actually, we could define a function which take input of the length of the work and the label of the work.
What do you mean the label? Oh, different labeling the whole work. Okay.
Yeah. And only two. And the function will give us the endpoint of the random walk endpoint. For example, we could implement a random walk like this, and this would be the endpoint. And also, it can be another endpoint if the length of the random walk is 3, and this is the endpoint for the random walk of length 4. Okay, so we can define such a function, and the query complexity and for evaluating this function, we need implement that many of random walks. So the query complexity of the time complexity of this for evaluating the function depends on the length of the random walk, and the output of the function output of the function is the endpoint of the random walk. So this is the function we are interested. So the problem is that whether we could find a relation R, which equivalents to find the negative edge. The main idea is that we could use okay, we can label sorry, the relation is that we can define a relation which contains the end point and the neighbor of the end point. Okay, and if so, we have the information of the endpoint of a random walk and its neighbor, and its neighbor. Then with this we can easily find the negative edge if there exists. You know the main idea?
Yes. So you need to like run the algorithm for each length of this walk,
Yes.
right?
Yes.
For certain level of walk, for certain pace,
yes.
And you need to check basically every step. You check different next. You check whether the endpoint, like the question I asked earlier, you check that endpoint, basically some vertex along the edge, whether they have the neighboring.
Yes.
And
but if the neighbor of these of the endpoints of the neighbor of the endpoint is the endpoint of a certain random walk.
another random walk.
Yeah, then we find the negative edge connecting these two random walk. Then we find its equivalent to find the collision for this function.
So, but in your like collision algorithm, actually you're finding fx and fx prime. So basically you are finding two walks, right?
Yeah.
So, but how? So you find which way you do first? You find two walks if they are satisfying certain relation, or you find the relation first.
Actually, the searching space is you can see the searching space is all of the length and all of the label of walks. And the output of the function is the endpoints and associated with the neighbor of these endpoints. And we define such a relation, which is if the neighbor of the endpoint contains some vertex which is in another endpoint of a certain random walk, then we call this is the relation we find.
So basically you search the space of different lengths, different labels.
Yes.
And you see whether certain two label and certain lengths, basically two vertex at different walks. When you find the 2 points, two vertex, do they satisfy the relation which they are within the labeling of each other?
Yes, and check the relation. Only use polynomial. The time for checking the relation is proportional to the number of vertex it's connect. The time for checking the relation is the degree of the graph. So which is independent of n. So we have this query complexity. Since the searching space is the labeling and the length of the random walk, and the number of labeling of random walk is square root of n, and the length of the random walk is 1 over poly epsilon. So in overall we can make a quantum speedup for finding such a collision by with this scale 2/3. Yeah, which is the query complexity showing here.
I see. But you must not only check whether they satisfy the relation. You must also check whether the link between them, the edge between them are negative, right? You still need to check this.
Yes, and that would not require a lot of time. Or the time to check the relation is independent of n, capital N.
I see. Okay, good.
Yeah, that is the main idea.
I see. Okay, thank you.
Thank you.
And so another remind, it seems that when you first time mentioned G1 and G2,
Okay.
The G1 is clusterable, but when you in this page is the opposite. So probably I think it's better to make it consistent, right?
It's 2.
Am I right?
2. Yeah, it's 2. It's 1.
Yes.
Yeah, something like this.
Okay.
Oh yeah. I think this is the typo, since in the manuscript G1 are far from classical.
Sorry, a final question. I understand how you use the collision algorithm to check whether it's clusterable, but I don't still get how you construct the one which is far from clusterable. How do you
how far
construct it? Yeah. How do you construct
that's
it?
for the classical result. There exists a algorithm for testing clusterability with this error.
So how do you actually construct it? I mean, I don't see.
Your question is why the classical algorithm is an epsilon clusterability tester, right?
Mm-hmm.
Actually, I did not check the detail of that paper, but actually they use the similar approach proposed by Goldrich in the pretty earlier paper. Yeah, it's the paper we are talking about, and they use the similar they use the similar approach comparing with these two papers.
Okay, I mean, I can see why you use the collision algorithm to check the clusterability using this quantum algorithm, but I don't see why you need to construct two different graphs in this case.
Oh, sorry. For the graph, for constructing the graph, that's for proving the query law bound.
Of classical?
Yeah, classical query law bound.
Since
we design two families of graph. They have distinct graph property. However, they cannot be distinguished by using square root of n queries. So it implies no algorithm can there's no clusterability tester can test these two families of graph or identify a now we can consider if we randomly pick a graph in G1 or G2 with equal probability, then if we have the clusterability tester, then it would show the clusterability tester would output would identify the graph is classable or not, or far from classable. Then the randomized algorithm or the clusterability tester can distinguish these two families of graph, which means it can distinguish them in not many queries.
You mean for the two graph, there is a lower bound square root of n for classical algorithm? But for any kind of graph, not necessarily these two, your quantum algorithm can actually achieve it in square root as 1/3 of n power of n to check. So not necessary for the two graph, for any graph, right?
Yeah. For algorithm, it can be applied for any sign graph, and for in order to derive the classical query low bound, we consider a hard instance which contains two families of graph. So it's two works, two results. Yeah, one is provides the such a hard instance. Another work is propose an algorithm that can be that can test clusterability for any sign graph.
I see. Okay, thank you.
Okay, thank you.
Okay. Do we have more questions? I guess this is a no. So thank you, Wojing, for presenting your work to us.